right. Alrighty, I got my thumbs up. Can people kind of hear now? You can hear? Excellent. Here we are on our computer science for the self-taught hacker. A brief introduction to CS with chipmunks. Or squirrel? Squirrel. Squirrel. That will be important later. It's a really pretty rat. So yeah, are you a programmer without a computer science background? So yeah, how many people here have a classic CS education? Okay, a few. A double E like myself, something close. Physics, econ, liberal arts, GED. Commenced from kindergarten at some point? All right. So let's, everything's on the computers now. So I know I spent a while as a self-taught guy thinking, oh my goodness, they know all this stuff, and what am I missing out on? And get a little chip on my shoulder. That 6502, I believe that's, we just saw that yesterday in the Atari talks. So if you were here for those. So our goal is, I'm not going to give you a year's worth of CS education as much as I might try, but hopefully I'll give you enough to get interested to learn more and to feel that it's not overwhelming. And maybe you've already got number 4 when you use a hash versus an array. At which point, I'm pretty much already done because you already know that. So a typical first year intro to CS, you need to cover algorithms and data structures and some computation theory. And before you can get started in those, you need some complexity analysis so that we can rate things so that then we can compare them, so that we can talk about stuff. And so that applies to the algorithms and to the data structures and the data structures that are used in the algorithms. Yes. So complexity, normally when people are talking about it, we've got big O and big omega and big theta, but really we only use big O. And even that we just use a little bit. But your first year CS, you pretend that that's the most important thing in the world. And that's what we will be doing today. Here's your little Wikipedia definition. May or may not be helpful. But it gets to the idea of it's how does something respond as we change the input size. And so what we need is a mathematical formalism because computer science, unlike programming, is about math and very little about computers. What we do all day is programming or engineering, depending on how much we have to deal with the real world. Computer science, not so much, but it's very helpful to teach us to inform our decisions. So for big O, the big thing is how does this scale as we do more of it? Does it scale up fast or slow? And really big O is, from a mathematical standpoint, G of n is an asymptotic upper bound if, C, some constant times G of n is bigger than f of n for all n greater than n naught. Yeah, that's when you're like, that's when you kind of glaze over and gloss over if you're trying to read someone else's CS stuff. A nice way to think of that is like you're in, it's an adversarial game. You get to pick G of n and C and some n, and then your opponent tries to pick the n bigger than the n you picked such that this isn't true. And that's what you'll be doing when you're trying to analyze what things are. But more usefully, let's look at some of the things that you will see. So the big O notation of something is stated as a capital O, big O, followed by some sort of equation function of n. An order of 1 means and really it just takes one operation, doesn't matter what else you have in there. Order of n, that's the baseline just to inspect all of your input. Order of n log n. If you're designing an algorithm, this is a beautiful spot to be. It's basically the free position. Once you're in n log n, you can sort your input for free-ish. And then if you can do your algorithm quickly on sorted input, then you can just do it that way. And then it's a fine line between n log n and n squared, and at that point, you're basically too slow. Yes, we have lots of quadratic equations for things. We would just like them to be faster. Then you get exponential and factorials, and you don't want those. I may even have a pretty graph where they show boom. Because once you have 10 things in 2 to the 10, you're at large. Is reasonable, but 1,000,000 things at 1,000,000 squared, yeah, you can do that. At 2 to the million, you're not going to be happy. So I realize that's a lot of hand waving over your big O. Yes, and that comes in handy both in the as you do your algorithms. This is the lovely slide from CS 161 at Stanford, which is an open available course from Professor Roughgarden, and it's quite good. He did it through open classroom at Stanford. The video there is pretty bad, but then he redid it with Coursera. I took it this fall. And I was taking it again just now to remind myself. And it's a wonderful course. Highly recommend it. Because it's what got me to think, oh, hey, I should come tell you guys this. So let's actually, that's a lot of words. Let's try and do something specific. So one of the first things that we analyze is a sorting algorithm. We like to start with bubble sort because it's conceptually very simple. For a bubble sort, you just walk through the array looking at 2 elements at a time. If they're out of order, you swap them. If you get to the end of the array and you haven't swapped any, then it's sorted. And what we'll see, let's see if this actually works. Oh, animated GIFs. Love it. So yeah, you just walk through, you sort it. The GIFs go really slow because to remind you that it's really slow. So it's bubble sort ends up being an n squared algorithm because you have to look, each pass through, you look at everything. You look at each pair of elements, so that's n operations to grab the n things. And then you have to do that potentially n loops through. So worst case scenario, they're all backwards, and you have to sort them all over and over and over again. It's just, I love watching it. All right. But it's very, what's nice about this is you can actually, right, you can sort of just work that out on your own, just walking through them. And the little person on the top has little tiny bubbles. Now, if we were to compare that, oh, hey, there's my other graph finally going. We'll just watch one sort because it's pretty. But so how we even figure out that that is too slow? I mean, it works when you're doing things by hand. I bubble sort my cards when I'm, I have 10 cards in my hand for a game of something. But I used to bubble sort them. And I found I do a merge insertion sort. But oops. All right. And it has times where it's useful. Like if your data is almost totally sorted and there's just a couple things it has to do, it's probably a good way to go. If you need to write a sorting algorithm right now while someone is over your shoulder, it's an okay way to go. Should you write your own sorting algorithm? No. There are people smarter than me and possibly you who spend their time making better sorting algorithms. However, it's useful to know what they are and how we compare them. So like if we were to look at Quicksort, Quicksort is a slightly more complex algorithm. I should actually step back for a second. I realized I forgot my algorithm slide. So what is an algorithm? It is a mechanical process by which you can go from an input to an output. That's the extent of the definition of an algorithm. It's a lot like a function conceptually. And so it's this series of steps, possibly recursively defined, that get you from your input to your output. So in the Quicksort case, we have a slightly more clever and more interesting algorithm. It's the first of what we would call a divide and conquer approach, wherein you take your problem and you split it into smaller pieces, and you keep splitting it until you have some sort of, you hit a base case, and then you build it back up. So for Quicksort, what one does is you pick an element that's your pivot, and then you walk through all the other elements, and if it's smaller than the pivot, you make sure it's to the left, and if it's bigger than the pivot, you make sure it's to the right. Then you take each of those halves, and you do that process again. And then once you've done that for all of them, you have a group of sorted lists that you just concatenate back together. So in each case, you look through all of the elements once, and you split it in half. So to analyze that, you see that since you split it in half each time, you can take a maximum of log base 2 of n steps. Step back and let that sink in for a second. So each time you cut it in half, so you go down by 2. That's all that's saying. So you do log base 2 number of steps, and each step you do n operations. So it takes n times a log base 2 of n. But we don't really care about our bases for big O notation. You get to play with the factors, and you drop all of the numbers, and you just end up with the powers. And so we call that a n log n solution. And I like Quicksort better than merge sort because it's easier to explain here on one slide. But those are two that you would see a lot. The problem with Quicksort, as seen in this pretty graph, is what its worst case scenario is you have to do n work, and if you split it into 1 and n minus 1, you end up splitting it into n cases, and so you do an n squared. And so that's bad in and of itself, and the fact that the case where that happens is if you're handed a sorted array. And so that's not so good. Versus if you pass bubble sort a sorted array, it just has to walk through and verify that it's good. What? Oh, yeah. It's also much more complex to imagine what it's doing when you're looking at it. Like I couldn't even tell you exactly what this picture is doing. Like the red, I believe, is the pivot that is moving, and then some of them are being rearranged, and then magically, it's like, oh, now we go do the top half, and then we split it, and we split it, and we split it, and there we go. And this is why we care. So you very rapidly, at 3,000 items to sort, at whatever units, this is in seconds, but of who knows what CPU, for this random graph. Is that really a 2,000? Sort versus still approximately 0 for a Quicksort, right? Now, if you did a chart of various n log n sorting algorithms, you would see that they have different slopes, but you don't want to be in that upper case there in your code. And you might inadvertently be doing that now, so hopefully we will touch on that. So for instance, again, what should you be using for sort? Probably something that's built in. So Perl sort, yay, Perl sort, actually has some things where you can tweak it, which, how many people knew that there was a use sort pragma where you could change how the sort worked? How many of those with your hands up worked on that? Because that doesn't count if you wrote it. Fun little piece of history. So Perl sort uses Quicksort and merge sort. Before 5.6, it was always Quicksort. And then in 5.8, we added merge sort. And I believe it actually does some clever heuristics to determine which one it's going to use. For instance, Quicksort is going to be faster for small lists in general than merge sort, but merge sort is stable, which means that if you give it a list and things have the same sort key, especially if it's a sub portion of the key, that things that have a particular order will maintain that order if they were in order. Okay, I'm going to skip that because that's difficult to explain. But so one of the things you can say is, hey, I want it to be stable, which means you're going to get merge sort. And you can explicitly ask for merge sort or quicksort. You shouldn't, but possibly for your data, that's the right choice. And the engineer would then say, well, go benchmark it. So the CS person says, let's analyze it, and then the programmer then has to get some data and benchmark it. And so the other thing we'll look into a lot, and I know I'm a little behind here, but data structures. And so we're just going to kind of fly through these. There's a lot of data structures that we look at first year and stuff. Arrays, lists, tuples, hash tables. In Perl, we have a couple of these built in. We have arrays, essentially. So arrays and lists are different. Based on their implementation, you have different behaviors. Is it a linked list? In which case, it's easier to add and remove things, but it's harder to get to any individual one. An array allows you to go directly to any element. So it's order 1 to look up an element. However, it's order n to see if a given element exists in the list. For a hash table, both of those are order 1. And that's why we use hash tables so often, because they're very useful for random access. And on CPAN, we actually do have a variety of libraries for trees and tries and some graph stuff and some sets. And when you need those, that'll be helpful. If you're over in Python land, you've got a built-in set. And so you see it used a lot more because it's there. And you can very easily use a hash as a set. But you're just wasting some storage space by having it point to something. But let's actually step back into an actual example. So a lot of you have played with or seen a Schwartzian transform. Anybody? At some point? Actually, who has never seen or heard of that particular transform? Excellent. Okay. So in the Schwartzian transform, the Lisp that we stole it from would just call it a DSU, a decorate, sort, undecorate. So the idea here is if you have a custom sort comparator that is somewhat expensive to run, in this case it's the foo function. So this is a faster version of just saying sort on, let's see here, foo of $A compare foo of $B. Of unsorted. Now, why is this faster? Goes back to our other issue of when we're doing a sort, we end up doing nlog and comparisons. And if those comparisons are expensive, that's a lot of computation. And so what we do here is we run that computation exactly n times, once for each element. Then we do some order 1 lookups to pull it out of an array and do the comparisons. And then we unmap it to remove that decoration. Now that is useful if calling foo is more expensive than the base setup time of building and tearing down this array. And there's actually a lovely wiki on this over at Wikipedia. And this is not my dog, but oh my God, that is adorable. So I hope you guys learned a little something from that. So yes, and so this is actually how knowing some of these things will help you in what you're actually doing day to day, which is you should be able to tell if you have an algorithm that's going to be really slow. If you look at your code and it's saying, is this element in this array over and over again, you're going to be very sad. And what I'm sadly not going to get to is my computation theory, including my halting state joke in honor of our keynote speaker today, Charlie Strauss, and author of a 2-book trilogy called Halting State. But computation theory is an interesting one, which is what can we calculate? What does it even mean to calculate? And we have the Church-Turing thesis, or Church or Turing, depending on who you talk to, which basically defines algorithmically computable if it's computable by a Turing machine, which is a very simplistic computer. And then we also prove that a Turing machine, anything that a Turing machine can do, any other computer can do because they're all equivalent. And it's much easier to reason about from a writing proofs standpoint. So when someone asks you about that, you at least have some idea what they're talking about, which is, oh, that just means it's computable. Yes, you can do it on a Turing machine. It's terribly inefficient, but we don't care about efficiency. And I'm wrapping it up. All right, so we will not get to P versus NP, which is a shame, because I've got a little proof. It fits on the side here. It's just not quite long enough. All right. And I have a whole bunch of links for you to learn more things. I totally recommend taking this course because it's awesome. There's some other fine papers to read. And I would open this up to questions, possibly one while they get the next person up here. Thank you so much for your time. Anybody? Questions? No. All right. Just remember, Simba loves you.